Dear colleagues, my name is Zixiong. I am from the School of Electronics and Information Technology, Yat-sen University. Today, my presentation topic is a new ensemble pruning method based on margin and diversity. My presentation will be divided into the following sections. Firstly, I will introduce the related background of our works. Secondly, I will show you the detail of our proposed method. Then I will present the simulation results, and finally, I will draw a conclusion. Now, let me introduce the related background at first. As we know, data classification is one of the main tasks of supervised machine learning. And ensemble learning has become a successful paradigm in the data classification field. Well-trained classifier can be obtained by exploring the distribution information in the training data, and then used to classify the samples of unknown categories. So the focus of our research is to obtain a set of well-trained classifiers, thus improve the final classification accuracy. Ensemble learning has attracted much interest in the machine learning community and has been applied widely in many real-world tasks. An ensemble is a set of learning models that make decisions collectively rather than relying on one single model. The success of ensemble methods is commonly attributable to two key issues: the accuracy of individual learners and the diversity among them. So the motivations of ensemble learning is to improve the performance of a single model, and then to reduce the likelihood of an unfortunate selection of a poor model. This is the schematic diagram of the decision boundary. Individual classifiers may only focus on part of the information on the decision boundary, which leads to certain limitations when making classification decisions. If the predicted information of multiple base classifiers can be integrated, a more reasonable classification result can be obtained. Although ensemble methods are effectual, one significant drawback here is that both the required memory and processing time increase visibly with the number of individual learners in the ensemble. To mitigate this shortcoming motivates ensemble pruning that aims to select a subset of individual learners in an ensemble, also named as ensemble selection or selective ensemble. Because it is not the fact that all classifiers used in the ensemble system can make the final classification results better. Now, let me show you the detail of our proposed method. In this section, a new ensemble pruning method based on margin and diversity, named EPMD, is proposed, which eliminates the useless base classifiers while improving the final accuracy of the ensemble learning framework. In order to solve the data classification problem effectively, the sample point near the classification decision boundary are more inclined to be focused on. Part of the original dataset is used as a training dataset to generate the base classifiers pool, and then a validation dataset is used to evaluate the generated base classifiers based on the proposed heuristic matrix. After obtaining the simplified subset of ensemble classifiers, classification tests are performed on the unused test dataset to obtain the final classification results. So the two main steps of our proposed method. One is to generate base classifier pool, and then to evaluate the base classifiers. Firstly, leaf and out class validation is utilized here to divide the initial dataset into three equal parts, which are used as a training dataset, validation dataset, and test dataset. Bootstrap method is used here to perform random sampling with replacement. Classification and regression tree named as CAIRT is utilized to train each training dataset. Then obtain the ensemble classifiers. CART tree is utilized here because it is more sensitive to the perturbation of the input data. It is easier to produce diversified base classifiers, and the computational complexity is not high. Each base classifier of the ensemble system is used to classify the validation dataset samples, and the majority voting is used here to obtain the prediction results. As we can see, a new unsupervised form of instances margin metric is proposed here to eliminate useless weak classifiers. For a sample point XIYI in the validation dataset, VC1 represents the number of votes of the class with the most votes. That is, the vast majority of base classifiers in the ensemble system classify and predict the sample XIYI into class C1. And VC2 represents the number of votes for the class with the second most votes, and so on. VCL represents the number of votes for the class label with the least number of votes. The number of validation dataset samples that are correctly classified can be obtained by the equation 2. And finally, we get the average margin value. Considering that the existing selective ensemble learning algorithms based on margin values rarely involve diversity between base classifiers, the Jensen-Shannon divergence is employed here from the perspective of information theory. The JS divergence measures the degree of difference between the probability distributions of the classification results of different classifiers. Eliminates base classifiers with low diversity, and improves the overall diversity of the ensemble system. When the JS divergence between two different classifiers in the base classifier pool is larger, it indicates that the information difference between the probability distributions of the corresponding classification results is greater. So finally, we will get the average degree of difference between the T-space classifier and the R-space classifiers, like the question 7. In order to take average margin and diversity contribution of the base classifier into consideration simultaneously, A trade-off between margin and diversity, named as TMD, is defined as an objective function, like here. By sorting all the classifiers in the base classifier pool in descending order, according to the obtained value, a new base classifier sequence can be obtained. Finally, by selecting the first S-base classifier that can maximize the average classification accuracy of the ensemble system on the validation dataset, a selective ensemble classifier subset can be obtained. The flowchart of novel method for ensemble pruning method proposed in this paper is shown in Figure 3. Here, we present the experiments and results. The experiments are run on 22 randomly selected datasets from UCI machine learning repository and Kio repository. This is the summary of UCI datasets used in the experiments. The initial ensemble classifiers scale is set to 200 base classifiers. The results of 100 repeated experiments are averaged to obtain the final classification accuracy. So we can see this is the number of samples, number of features, and number of classes. Average classification accuracies of 5 ensemble pruning methods on 22 test datasets are given in Table 2. The results with better performance of the proposed method are highlighted in bold. For most datasets, the method proposed by this paper can show better classification performance compared with bagging and other 3 ensemble pruning methods. In addition, this experiment also calculated the size of the classified subset of ensemble pruning and compared the 4 selective ensemble classification algorithms. The running speed of the ensemble learning method mainly depends on the complexity and number of the base classifiers in the ensemble system. As the number of base classifiers in the ensemble model continues to increase, the running time consumed will also become longer. It reveals that using the method of our proposed method can significantly reduce the number of base classifiers in the ensemble system, and thus reduce the computational cost. Here we draw our conclusion. In this paper, we proposed a novel ensemble pruning algorithm, or selective ensemble algorithm based on margin theory and ensemble diversity, named as EPMD. This method presents a new unsupervised form of average sample margin measurement criteria. It considers the margin distance from the unknown data samples to the classification decision boundary, and then characterizes the overall performance of the classifiers in the ensemble system according to the sample's margin values. In addition, the JS divergence of the classification results is calculated with respect to the probability distribution of the class labels and used to evaluate the diversity of the base classifiers in the ensemble system. Or in conclusion, our idea comes from the fact that the combination of a large number of base classifiers is not always a perfect ensemble, and the relatively few excellent classifiers with diversity are sufficient to obtain the best generalization performance. These are the selected references. Thanks for your listening.